Right, in the last lecture, we had the chance to look at the very first few concepts that we covered in mechanics of materials. In particular, we started by looking at the connection between statics and mechanics of materials. And then we also looked at what type of stress we have for each type of load that we can apply on a certain structure. So we looked at axial load, torsional load, bending moment, and shear force, and then we saw what kind of stress we have again in a structure because of these types of load. So today we will move a little bit forward, and we will start to look at the connection that we have between the loads, the way how the stress is distributed along the cross section of the beam, and also we will look at what kind of deformation we have because of each specific type of load. So we will start by looking at the axial load. All right, axial load is a force. We already said that when we have an axial load, we have a normal stress that we indicate with sigma. And the way how we calculate this stress is equal to P over A. P is the intensity of the axial load, and A is the area of the cross-section. If we look at the distribution of the stress along the cross-section, so this will be the side view of the cross-section, we can understand that this equation doesn't give any indication of the location at which we want to determine the stress, which means that this sigma equal to P over A would be valid here, for example, also here, and also here. So for every location within the cross-section, we have the same value of the stress due to a certain axial load, which means that the stress is an homogeneous stress, is constant within the entire cross-section. So, for example, let's assume that in 3D we have a square cross-section. I mean, that looks like this. We will have at every point along within the cross-section the same value of the stress. So it doesn't matter where we calculate the stress, this stress will be always the same. All right, regarding the deformation, when we have an axial load applied on our beam, we have an elongation or contraction. Elongation means that the beam becomes longer. Contraction means that the beam becomes shorter. So the way how we indicate the displacement is with the Greek letter delta. And the equation that we use to calculate the displacement is P L over A E, where P is the amount of the load that we apply on the beam. L would be the length of the beam. A is the area of the cross section, the same A that we have here, and E is the Young's modulus of the material that we have for the beam. So in this case, basically we can understand that to determine the displacement of the beam, we need to know the geometry. So we need to know A and L. We need to know what kind of material we have for the beam, and of course we need to know the load that we apply. Whereas when we have to calculate the stress, we need to know only the load and the cross section. We don't need to know what kind of material we have in order to determine the stress, but we need to know what kind of material we have to determine the deflection. So the second load that we can look at is the torsional load. All right. In this case, also, we know that to calculate the stress, first of all, what kind of stress we have is the shear stress. And the equation that we use to calculate the stress due to a certain torsional load is T over J times C. So this is an equation that is valid for circular cross sections. So if we indicate our cross section like this, by looking at the equation, we can determine what kind of stress distribution we have. So in this case, we have one parameter, which is the parameter C, that actually tells us, gives us some indication on where we want to determine the stress. So this parameter here is the distance between the axis of the beam, which will be the center of this cross section, and the location at which we want to determine the shear stress. So this means that when we are on the axis of the beam, this parameter will be 0 because there is 0 distance, which means that the stress will be 0 as well. So when we move far away from the axis of the beam, it means that this parameter C increases as well. So it means that the shear stress increases as well. The maximum value of C that we can have occurs at the edge of the beam. So it means that at the edge of the beam, we have the maximum value of C, which means that we have the maximum value of the shear stress. So if we have 0 stress at the axis of the beam, and we also have the maximum stress at the edge of the beam, we also know that this parameter is a linear parameter. We can simply connect these 2 points, and then we obtain the distribution of the shear stress due to a certain torsional load. So even in this case, we can look at the deformation that occurs when we have a certain torsional load. And the deformation is, in this case, indicated with the Greek letter P, and is the angle of twist. So the equation that we have to use to determine the angle of twist is the following: is TL over J. So by looking at this equation here, we can see a very strong analogy with this equation here. And because if we look at the 2 equations, physically are actually identical. Because as you can see here, we have P, which is the load, and here we have T, which is the load. Then we have L, which is the length of the beam, and here we also have L, which is the length of the beam. Then here we have A, which is the area of the cross section, and here we have J, which is the polar moment of inertia. So both of them are properties of the cross section. And then here we have E, which is the Young's modulus of the material, so a property of the material. And here we have G, which is the shear modulus of the material. So it is also a property of the material. Keep in mind that these 2 equations are equations that we can use only when we have a circular cross section. So the next equation that we can look at is the equation that that is responsible for determining the stress due to a certain bending moment. All right, in this case, the equation that we use is the flexure formula, we know that when we have a certain bending moment, we have normal. So when we have pure bending moment, we have a normal stress. And the equation that we use is m over I times c. So now we can look also at the way how this stress is distributed. So if this is the side view of the cross section, we can analyze this. We can analyze this equation to determine how the stress is distributed along the cross section of the beam. So we can look at this equation, and this equation is basically analogous this time to this equation here. They are both related to a certain moment applied on a beam. In this case, we have the torsional load, so we are twisting the beam. In this case, we have a bending moment, so we are bending the beam. So here we have shear stress. Here we have normal stress. Here we have the load that we apply, which is the torsional load. Here we have the moment that we apply, which is the bending moment. Then here we have I, which is a property of the cross-section, the moment of inertia. Here we have J, which is also a property of the cross-section, the polar moment of inertia. And then here we have C and C, which are both distances from an axis where there is no stress. So in this case, this is the distance between the point where we want to determine the stress and the center of the axis. Here is the distance between the point where we want to determine the stress and the neutral axis of the beam. So in this case, the distribution of the stress is linear, exactly like it was here. And we have zero stress at the neutral axis and maximum stress when we go away from the neutral axis, which means at the edges of the beam. So in this case, we have that the top fibers are stretched and the bottom fibers are compressed. Of course, this depends on what kind of, what sign of moment we apply. So for example, if this is the original configuration of our beam, if we apply a moment in this direction, we obtain a deformation that looks like this. And we have top fibers that are stretched and bottom fibers that are compressed. On the other hand, if we apply a bending moment in the opposite direction, looks like this, we will obtain opposite deformation. And in this case, we have top fibers that are stretched, excuse me, bottom fibers that are stretched and top fibers that are compressed. All right, we can now look at the last load that we can apply on a certain beam, which is the shear force. So we know that when we apply a shear force, we have a shear stress. And the equation that we have to use in order to determine the shear stress due to the shear force is the shear formula. And it is given by V Q over IT. So in this case, it is a little bit less intuitive to determine the distribution of the shear stress due to the shear force. And this is due to the fact that we have basically this term here that is the static moment of the portion of the section above the location at which we want to determine the shear stress. So this term here, again, the static moment, is given by the product between a certain area and a certain distance. So these two parameters, the area and the distance, involve the geometry of the cross section, basically the width and the height, and then basically again by multiplying these terms here, and then we bring inside the shear stress equation, the shear formula. Basically, eventually we obtain a quadratic distribution of the shear stress. So if this is so if this is the side view of the cross section, and this is also the neutral axis, again the quadratic distribution looks like this. Again, this is the quadratic distribution that we have for a simple rectangular or square cross section. If we move to more complex cross sections, for example, if we have a cross section that has an I shape, so if we have this cross section, the side view looks like this. We also have the neutral axis in the middle of the cross section, assuming that we have a symmetric cross section, and then the distribution in this case looks like this. So in this case, it is still a quadratic distribution, but since we have a change in the thickness from the top flange to the web, and then from the web to the bottom flange of this cross section, we also have a jump in the intensity of the shear stress due to basically this term here as well. But in general, we have a quadratic distribution. Something that I think is important to notice is that when we compare these two equations, they basically give an opposite behavior in terms of location in terms of magnitude of the stress at a certain location. So in this case, when we look at the flexor formula, we have that the stress is 0 at the neutral axis. When we look at the shear formula, the stress is actually maximum at the neutral axis. If we look at the top and the bottom edge of the beam, we have that from the flexor formula, the stress is actually maximum. If we look at the shear formula, the stress is actually 0 at the top edge and the bottom edge. So these two equations give us a kind of opposite result, especially when we want to identify where the maximum stress is. So the last thing that we can look at, as we did for the other two loads, we looked at the deformation due to a certain axial load, the deformation due to a certain torsional load. In this case, we can also look at the deformation due to a certain transverse load or bending moment. These two are related to each other. And in order to determine this deformation, which is the deflection, we have to calculate, we have to look at the equation of the elastic curve. So basically, the equation of the elastic curve is an equation that relates several parameters to each other. So the parameters that are related through this equation of the elastic curve are we have v lowercase v of x, theta of x, m of x, v uppercase v of x, and w of x. So let's look at the meaning of all of them. So we have v of x is the deflection. And basically this tells us the distance in the vertical direction between the original configuration and the configuration after the deformation at when we apply a certain transverse load. So this is the deflection. Then we have this parameter here that is the rotation. This tells us the rotation of the beam after we apply a certain, excuse me, the rotation of each cross section after we apply a certain load. Then we have the bending moment. So how the bending moment is distributed along the cross section. Then we have the shear force. And then we have the transverse load. So all of them are functions of x, which is the axial coordinate, and the equation of the elastic curve should be written like the equations of the elastic curve should be written like this. All right, here we have that the first derivative of the deflection with respect to the axial coordinate is equal to the rotation. Then we have the second derivative of the deflection with respect to the axial coordinate is equal to the moment, the distributed bending moment, and EI. I is always the moment of inertia, and then E is also the Young's modulus. Then we have the third derivative of the deflection with respect to the x coordinate is equal to the shear force distribution divided by EI. And then we have that the fourth derivative of the deflection with respect to the axial coordinate is equal to the distributed load divided by EI. So basically, by using these equations, we can determine the deflection of the beam. So, for example, if we have a certain a cantilever beam and we apply a certain load, let's say P, we will have a deformation. In this case, would look like this. And then this deflection here, which is basically the quantity that we are interested in when we want to look at the deformation due to a certain transverse load, would be this distance here. From this point to this point, at this value of the axial coordinate. If we look at another value of the axial coordinate, for example, here, the deflection would be this one. At this point of the axial coordinate would be this one, and so on. That's why V, the deflection, is a function of the axial coordinate, because for every value of the axial coordinate, we will have a different value of deflection. And if we know again how the load is distributed, we can apply this equation here so that we can basically integrate this function 4 times, and we obtain the deflection. If we know, for example, how the load is distributed, excuse me, how the shear force is distributed along the cross section, we apply this equation here. We need to integrate 3 times, and we apply and we obtain the deflection. If we know how the moment, the bending moment, is distributed along the cross section, we can integrate twice this equation here, and we can obtain the deflection as a function of x. Typically, we use either this equation here, if we are able to easily determine the equation of the bending moment, or we can use this equation here if we know how the load is distributed along the cross section.